Welcome to our deep dive, into this fascinating world where logic and games collide. We've got some excerpts from the Stanford Encyclopedia of Philosophy's entry on logic and games. And today we're going to explore this kind of intriguing intersection.
Yeah, it's a really fascinating area. We'll be looking at how game-like elements have been a part of logic for a long time, throughout history, really, and how these connections have led to some pretty amazing insights, actually.
I'm excited. I'm ready to level up my logic skills.
Yeah.
The source mentions Aristotle using debates like games. Is that where this all started?
Yeah, you could say that. Aristotle's work on syllogisms was very closely connected to his study of debates. He saw them as structured exchanges where the goal was to, reach valid conclusions through a series of moves, almost like a game. And this perspective even kind of shaped how logic was viewed during the medieval times, when it was often called dialectics.
So from the very beginning, there was this idea of logic as like a dynamic process, a back and forth.
Right.
The source mentions dialogues being used to teach logic way back then.
Yeah, dialogues were a popular way to teach and test logical concepts in medieval times. They provided a more interactive and engaging way to learn. They encouraged students to think critically and to refine their reasoning skills.
Makes logic sound a lot more fun than just memorizing all those rules.
Right.
I wonder if those medieval students ever felt like they were actually playing a game while they were debating.
It's possible, and this playful approach to logic isn't just in ancient times. Even Lewis Carroll, the guy who wrote Alice's Adventures in Wonderland, he wrote a logic game called The Game of Logic in the late 1800s.
Okay, so this connection between logic and games has been around for a while.
Yeah.
But the source also mentions a link to modern game theory.
Oh, absolutely. A lot of the pioneers in game theory, like John von Neumann and Willard Quine, were also logicians. They saw how games could provide a way to understand how people make decisions strategically, which is closely related to, logical reasoning.
So these early game theorists were onto something big.
They were. And that connection just got stronger. For example, Leon Henkin proposed using games to interpret sentences in infinitary languages, languages that can express infinitely long sentences. And this was a huge leap forward. It really pushed the boundaries of how we could analyze these complex logical statements.
Wow, using games to tackle infinity, that's pretty ambitious. But were all logicians, happy about this whole game-based approach?
Not really. At the beginning of the 20th century, there was a big focus on being very rigorous and formal in logic. Some logicians thought that using games to understand logic was a bit frivolous. The intuitionist Delia J. Brower even criticized its approach, saying that it let mathematics degenerate into a game. His quote reflects how skeptical some people were about games and logic.
So it wasn't all fun and games getting this idea accepted in logic.
No, it took some time. It wasn't until the 1960s that people started to see the value in using games as logicians began exploring more practical techniques and saw the real benefits these games could offer.
Like they finally realized that games could unlock a whole new level of understanding. Okay, so we've seen how games have been part of logic throughout history. But what exactly is a logical game? How do you actually play logic?
At their core, logical games usually involve two players, often named Abelard and Eloise, who are making choices from a set of options called a domain. They take turns selecting elements from this domain, creating a sequence of choices. This sequence, which can be finite or infinite, is called a play of the game.
So it's a bit like chess, where each move contributes to the overall, flow of the game.
Exactly. And here's where things get really interesting. Each logical game has specific winning conditions that determine which player wins based on the sequence they create. Think of it like the rules of the game.
Gotcha. So the players are strategically making choices, trying to steer the sequence towards a win. What kind of winning conditions are we talking about here?
It could be anything. Maybe Abelard needs to get a certain pattern to appear in the sequence, or maybe Eloise wins if the sequence goes on forever. And of course, each player will try to use a strategy, like a set of rules for their choices, to secure a win.
So having a winning strategy means you're basically unbeatable, right?
If such a strategy exists, then yeah. And if one of the players has a strategy that guarantees they'll win, we say the game is determined.
Makes sense. So are all logical games determined? Is there always a sure winner?
That's a great question, and it leads us to a pretty big discovery. In 1953, Gale and Stewart proved that not all games are determined. Sometimes, no matter how smart they play, neither player has a guaranteed way to win.
Wow. So even with perfect logic, you're not guaranteed to win. That's kind of unsettling.
Right.
What does that even mean in the context of logic?
It means that even in systems governed by logic, there are some things we just can't predict. This discovery was a big deal in the world of logic, especially in set theory. It made people rethink some of the most basic ideas they had.
Okay, so we had these logical games with players making choices and trying to win based on certain conditions. Sometimes there's a guaranteed winner and sometimes not. But from a philosopher's point of view, why do we even care about winning in these games? What's the bigger picture here?
That's a question that philosophers have been thinking about for a long time. It's sometimes called the Dawkins question, after the biologist Richard Dawkins, who asked a similar question about games and evolution. When talking about logical games, it comes down to this. What does it even mean for a player to win in a logical game? And how does that help us understand logic and reasoning?
That's a deep question. It's like we need to connect these abstract games to the real world of logic and thought.
You got it. And finding a satisfying answer to the Dawkins question can be a real challenge. It forces us to really think about some fundamental questions about truth logic and what it means to think rationally.
Okay, so we have this framework for logical games,
Mm.
but how do we actually use them to understand something like classical logic? The kind of logic we use in everyday life.
Well,
How do those connect?
that's a great question. Welcome back to our deep dive into this fascinating world where logic and games come together.
I'm still thinking about all those incredible connections we've uncovered. Who knew games had such a deep link to the history of logic?
Well, get ready to go even deeper. We're going to explore how mathematicians actually use games to build and analyze complex structures. These games aren't just about playing with logic, they actually create logical structures.
That sounds really powerful. It's like using games as blueprints for building logical well structures.
That's a great analogy. Let's start with forcing games. They're a bit like a group of builders working together on a house. Each builder, represented by a player, usually Eloise has a specific job. One handles the plumbing, another one does the electrical, and so on. The goal is to show that they can finish their task no matter what obstacles the other players representing Abelard throw their way.
So it's a collaborative construction project,
Sure.
but with logic as the building blocks.
Exactly. To prove that the house, which is our logical structure, can be built, we need to show that each builder has a winning strategy. If each Eloise can succeed no matter what the Abelards do, then we know the structure can be built even if it's infinitely complex.
That's a mind-boggling concept.
Huh.
We're using games to demonstrate the existence of structures that could be infinitely complex.
Yeah. Precisely. Forcing games have been crucial in proving important theorems in model theory, like the Lomenheim-Skolem theorems, which deal with different sizes of models for a certain logical theory.
Okay, so we're not just playing games with logic, but actually using them to build and prove the existence of these intricate logical structures. That's amazing.
It is. And now for another game with a pretty delicious analogy, cut and choose games.
Ooh, this sounds more my speed. Does it involve actual cake?
Well, imagine you're cutting a cake into two pieces and I get to pick which piece I want. The simple act kind of forces you to divide the cake fairly, wouldn't you say?
Absolutely. I wouldn't want to end up with a smaller slice.
Exactly. Mathematicians take this idea and, well, they do what mathematicians do. They take it to the extreme. Imagine this process happening over and over again infinitely, or even starting with an infinite number of pieces to begin with.
Now, that's just showing off.
Maybe. But these cut and choose games tell us a lot about how definable sets are structured and how complex they can be. The cutting is like applying a property to make a subset, and the choosing is like picking one of those subsets. When we analyze these games, we get some interesting insights into what definitions and sets actually are.
So even something as simple as cutting a cake can have some deep implications for logic and set theory. I'm starting to see a pattern here. Deceptively simple games leading to some pretty complex insights.
You got it. And speaking of deceptively simple, have you ever heard of the tree of two successor functions?
Can't say I have. Does it bear fruit?
Not quite. Imagine a tree that branches out forever in two directions at every point. You can think of it as moving left or right from any spot. This structure seems basic, but it's actually super interesting from a logical perspective.
So it's like a binary tree that goes on forever.
Exactly. There's this amazing theorem by Michael Rabin that says we can determine if any sentence in monadic second-order logic is true within this tree. This type of logic lets us talk about not just single elements, but entire sets of elements, which makes it very powerful.
So even this seemingly simple tree can handle some pretty sophisticated logic.
Exactly. And the original proof of Rabin's theorem was really dense and complicated. But then Yuri Gurevich and Leo Harrington and independently Andrei Muchnik, they all found a much simpler proof using, you guessed it, games.
Of course, games always seem to simplify things. How did they do it?
They created a game where one player acts like an automaton, which is a theoretical machine that processes information. When they analyzed the strategies in this game, they made Rabin's theorem much easier to understand, and it made a lot more sense. This shows another really powerful aspect of logical games. They can make complex ideas much easier to grasp.
So games aren't just for solving problems in logic, but they're also for explaining those solutions in a way that makes sense. It's like they provide a bridge between abstract ideas and ideas we can understand.
That's a great way to put it. Games let us visualize and interact with complex concepts, and that makes them much more illuminating. This deep dive is starting to feel like its own logic puzzle game. We're uncovering all these hidden connections and unlocking new levels of understanding with every game we look at.
I like that. And speaking of unlocking new levels, let's move on to a different kind of games with a long history, games of dialogue, communication, and proof.
Okay.
This sounds like we're getting into how logic works in actual debates and arguments.
You're on the right track. Our journey takes us back to the medieval period to a specific type of debate called obligations.
Obligationes, that sounds intense.
It was. Imagine two debaters, the opponents and the respondents. They're locked in this battle of wits. They would start with a statement, often a false one, called a positum, and the respondents had to defend it against the opponent's challenges, but they had to stay logically consistent the whole time.
So the respondents is trying to build a logical fortress around this potentially flawed idea, while the opponent is trying to tear it down.
Perfect analogy. The opponent's goal was to force the respondents into a contradiction to expose the flaws in their reasoning. These debates were really about exploring the nuances of logic, not so much about figuring out who was right or wrong.
Sounds like a fascinating mix of logic strategy and just good old-fashioned verbal sparring. Did anyone ever try to formalize these obligations debates into actual logical games?
While obligations themselves weren't actually formal logical games in the way we think of them today, they did pave the way for games that model the process of proving a logical statement. A key figure here is Paul Lorenzen, who introduced dialectical games in the mid-20th century.
So he took the core idea of those medieval debates and gave them a modern, well, a formal structure.
Exactly. In Lorenzen's games, there's a proponent who defends a logical statement and an opponent. These games and the many variations of them let us see logical proofs as dynamic processes of argumentation instead of just static objects.
So instead of just seeing the end result of a proof, we're seeing the step-by-step process of how it's built through this back and forth.
Exactly. This new way of looking at things has become super important in modern proof theory. We now talk about the semantics of proofs, which means giving meaning to each step in the process of creating a proof.
That makes a lot of sense. We're not just proving things, we're trying to understand how the very act of proving works, the give and take of how logical arguments are built. But I'm curious, going back to the Dawkins question we talked about earlier, what does it really mean to win in these dialogue games?
Yeah.
Who are the players supposed to represent, and what's their goal?
That's a question that has caused a lot of debate. Some people argue that the proponent in Lorenzen's games is like an idealized mathematician who's carefully building a proof step by step. Others see it as a model for how rational discussions should work, aiming to reach agreement through logic and reason. There's no one right answer to the Dawkins question for these games, and it remains a pretty big philosophical challenge.
So even with these clear rules and connections to formal logic, there's still room for philosophical debate about what these games actually represent on a deeper level.
Absolutely. The formal aspects of logic and the philosophical aspects are very closely connected. The games give us a concrete way to explore logical concepts, but they also make us ask some pretty deep philosophical questions about truth proof and what it means to argue rationally. They make us think about logic in new and sometimes challenging ways.
It's like these games aren't just tools for doing logic. They're like invitations to think about logic in a much deeper way.
That's a fantastic way to put it. They challenge us to rethink what we assume about logic and to consider different perspectives on how it works in various situations. And speaking of different situations, there's a whole other category of games that dive into the really complex world of logic with limited or imperfect information.
Oh, that sounds like a whole other level of complexity. I'm ready to take on the challenge.
Right. Let's explore this fascinating world of imperfect information games and see what new insights we can find.
Welcome back to the Deep Dive. We've traveled through history, we've explored how logical structures are built, and we've even talked about those medieval debates. Now, I'm really curious about those games with imperfect information you mentioned.
Yeah.
I feel like they could really change things up.
Oh, they definitely do. Games with imperfect information are a lot like the challenges we face when we're reasoning in real life. We often have to make choices without having all the information. They force us to come up with new strategies and to deal with the fact that we can't always predict what's going to happen.
That sounds kind of scary, but also really exciting.
Yeah.
Can you give me an example of one of these games?
Sure. Imagine a simple game where Abelard has to pick either 0 or 1. Then Eloise, without knowing what Abelard chose, also has to pick either 0 or 1. Eloise wins if they both pick the same number. Now, even though this is a very short game, neither player has a guaranteed winning strategy.
So even if they use perfect logic, they can't guarantee a win. That's kind of unsettling. I guess that's what makes these games so interesting, though.
Exactly. And this leads to something really fascinating. That famous Gale-Stewart theorem we talked about earlier. That theorem says there's always a winner in certain types of games with perfect information. Well, it doesn't work when we have imperfect information. It's like the rules of the game completely change.
So now we're in a world where even the most logical approach might not lead to a result you can predict. That has to have some pretty big implications for how we think about logic and reasoning in general, doesn't it?
Absolutely. It really highlights the fact that in so many real life situations, we have to deal with uncertainty and not having all the information. And that's where a type of logic called independence-friendly logic or I-level logic comes in. It's specifically made to deal with these kinds of situations.
How does IA logic even work? Does it somehow account for this missing information?
It does. IF logic lets us express the idea that a choice should be made without depending on some of the choices made before. For example, a sentence in IF logic might say, for every number x, there's a number y, independent of x, such that.
So it's like we're building the idea of limited knowledge right into the language itself.
Exactly. And this has some pretty interesting consequences. Remember how we talked about strategies in logical games? Well, in games with imperfect information, we have to restrict those strategies to reflect the fact that the players don't know everything.
It's like we're tying one hand behind a player's back to simulate not having all the information.
In a way, yeah. Now, one really cool thing that happens in these games is something called signaling. Think about a game like Bridge, where partners have to communicate with each other through their moves. They're kind of hinting at the cards they have without actually saying what they are.
So even with limited knowledge, players can still try to share information through their choices. That makes the game even more strategic.
Exactly. This brings up a really fascinating philosophical question. Is imperfect information really a part of the game itself? Or is it more about the limits we put on the player's strategies?
Okay, I'm sensing a bit of a philosophical brain teaser here. Can you explain that a bit more?
Well, intuitively, we tend to think of imperfect information as part of how the game is set up, not something about the strategies themselves. But when we formally define imperfect information in game theory, we do it by restricting the strategies. And this can lead to some surprising things happening.
Can you give me an example of one of those surprising things?
Consider this sentence in IF logic. There exists a number x, and there exists a number y independent of x, such that x equals y. Now, you might think that if Eloise can't remember what she chose for x when she's choosing y, she can't possibly win. But surprisingly, she actually does have a winning strategy. She can just always choose 0.
Wait, what? How is that possible if she doesn't know what X is?
It's because even though she doesn't remember the specific number she chose for x, she can still follow a general rule that guarantees she'll win. This shows us the difference, a subtle but important difference between how we normally think about imperfect information and how it's formally defined using strategies.
Okay, my brain is doing flips right now. But this brings up another question. If we're working with logic where information is limited, how do we even define what a sentence means in that context? Like in classical logic, we have Tarski's definition of truth. Is there something similar for IF logic?
That's a great question. For IF logic and systems like it, we have to shift our perspective a little. Instead of asking when a single assignment of values to variables makes a formula true, we start looking at sets of assignments, which are called teams. This was pioneered by Juho Väinö, who developed a whole bunch of logics that focus on these teams and how variables depend on each other.
So it's like we're going from individual truths to truths that hold within a group of possibilities.
Exactly. This shift to what's called team semantics has opened up some really exciting new areas in logic. It lets us explore the idea of dependence in a much richer way. We can even introduce new logical atoms that directly express dependencies, like x depends on y, or x and y are independent.
Wow, this whole exploration of imperfect information games has taken us to some pretty deep philosophical and mathematical places. It's amazing how these games keep showing us new layers of complexity and making us rethink these fundamental ideas.
It's been quite a journey, hasn't it? From ancient debates to games that model how computers work, and now to these really interesting games with imperfect information. We've seen how games can help us understand the complexities of logic and reasoning in so many different and often unexpected ways.
I have to say, this deep dive has really opened my eyes. I'm starting to see games everywhere I look, not just as entertainment, but as powerful tools for understanding how we think and make sense of the world. Any final thoughts for our listeners as we wrap up this exploration?
I'd encourage everyone to keep exploring this fascinating world where logic and games meet. Whether you're into the philosophical puzzles, the mathematical challenges, or just the fun of playing around with ideas, there's a game out there waiting to engage your mind and make you curious. So keep playing, keep exploring, and keep those logical muscles working.
And that's a wrap on our deep dive into logic and games. Thanks for joining us on this adventure. Until next time, keep those minds sharp and those game boards ready for action.